Welcome to Learn with us. This is the 20th lecture of Basic Electronics.
First, we will have a quick review of our previous lecture. In your last lecture, you studied about collector characteristic curves and you also understood effect of temperature on these curves. In your previous lecture, you also understood what is DC load line and what is early effect. What are the learning objectives of this lecture? In this lecture, you will understand small signal or AC analysis of bipolar junction transistors. In this lecture, you will also derive equations of small signal collector current, small signal base current, and small signal emitter current. Now we will understand small signal analysis of bipolar junction transistors, which is also known as AC analysis of BJTs. Small signal analysis allows us to do linear analysis of transistors. Now, if you have a transistor configuration like this, and the arrow is here, it means this is an NPN transistor configuration where we have RC here, here we have VCC supply voltage, and as you can see this source is connecting base and emitter, so and it is a DC source as well, so we can write it like this, okay, because we know that DC quantities are written in uppercase with uppercase subscript, okay. Now as you can see in this circuit we have only this DC source here, okay. So we will write these currents in uppercase with uppercase subscript. Here we have this DC base current and here we have this DC emitter current. We know that here we have voltage VCE, okay. Now look at this configuration. Now again we have arrow here, it means it is an NPN transistor configuration as well, where here we have supply voltage VCC, here we have RC, this is the direction of collector current, this is the direction of base current, and this is the direction of emitter current. Here we have this source and here we have this another source. Now we know that this is a DC source and this is an AC source, okay. It means here we are talking about instantaneous quantities. Now what are these instantaneous quantities? These are the quantities that are measured at a particular instant and they are sum of DC quantities and time varying or AC quantities. It means here we have collector current, which is sum of DC collector current and AC collector current, because we know that we write AC or time varying quantities in lowercase with lowercase subscript, and this is a DC quantity which is written in uppercase with uppercase subscript. So this instantaneous collector current will be like this. It means it is written in lowercase with uppercase subscript. Now what about instantaneous base current? It will be like this, means it is the sum of DC base current plus time varying base current. Now what about emitter current? It is the sum of DC emitter current plus time varying emitter current. It means here we'll write this instantaneous collector current. Here we have instantaneous base current and here we have instantaneous emitter current. Now what about these sources? We know that here we have this VBE, it means it is a DC source, and here we have this VBE, it means it is an AC source written in lowercase with lowercase subscript. So the instantaneous source will be VBE is equal to DC source plus AC source. Means these are instantaneous quantities and they are sum of DC quantities and time varying or AC quantities. Okay. Now we will understand small signal collector current. We know that the equation of DC collector current is IC is equal to IS e raised to the power VBE divided by NBT. Here this N is 1. It means now this equation becomes IC is equal to IS e raised to the power VBE divided by VT. Now as you can see here, this collector current and this VBE, they are DC quantities written in uppercase with uppercase subscript, and we call this equation number 1. Now here we are talking about instantaneous quantities. So instantaneous collector current will be written as IC is equal to IS e raised to the power instantaneous base to emitter voltage divided by VT. Now as you can see here, instantaneous quantities are written in lowercase with uppercase subscript, and this is equation number 2. Now we know that this instantaneous base to emitter voltage is the sum of DC base to emitter voltage and AC or time varying base to emitter voltage. Now if we substitute this value of instantaneous base to emitter voltage here in this equation number 2, we get instantaneous collector current is equal to IS e raised to the power DC voltage plus AC voltage divided by thermal voltage. Okay. Now if we open this bracket, we get instantaneous collector current is equal to IS e raised to the power DC base to emitter voltage divided by VT multiplied by E raised to the power AC base to emitter voltage divided by VT. Now we know that this whole term is equal to DC collector current, as you can see here in this equation number 1. So now this instantaneous collector current is equal to DC collector current multiplied by E raised to the power AC base to emitter voltage divided by thermal voltage. Now this is equation number 3. Okay. Now from power series expansion formula, we know that E raised to the power x is equal to 1 plus x square divided by 2 factorial plus x cube divided by 3 factorial and so on. Now if we apply this power series expansion here to this equation, and if we assume that here this VBE is very much less than this thermal voltage, it means here we will neglect higher order terms. So now this equation number 3 becomes instantaneous collector current is equal to DC collector current, and here we have 1 plus AC base to emitter voltage divided by thermal voltage. Now if we open this bracket, we get instantaneous collector current is equal to DC collector current plus IC VBE divided by Vt. Okay, we know that instantaneous quantities are sum of DC and AC quantities. It means here this quantity is DC quantity and here this is an AC or time varying quantity. It means it is IC, because we know that AC or time varying quantities are written in lowercase with lowercase subscript. So this is small signal collector current, which is equal to IC VBE divided by VT. Okay, so now this is the equation of small signal collector current or small component IC. From our previous slide, we have derived the equation of small signal collector current, which is equal to IC VBE divided by VT. Now here this IC divided by VT is equal to GM. Now if we put this value here in this equation number 1, we get IC is equal to GM VBE. Now what is this GM? This GM is transconductance, which is the ratio of DC collector current and thermal voltage. As you can see here, this transconductance is directly proportional to DC collector current and it is inversely proportional to thermal voltage. So what will be the unit of this transconductance? The unit of this transconductance will be milliamperes divided by volts. So now this is the equation of small signal collector current in terms of transconductance. Now look at this example. If you have collector current which is 0.5 milliamperes and if you want to find the value of transconductance, so how you are going to find this value? You will use this formula Gm is equal to IC divided by Vt. We know that the value of thermal voltage is 0.025 volts. Now, if we put these values of collector current and thermal voltage in this formula, we get Gm is equal to 0.5 milliamperes divided by 0.025 volts, and after solving this you will get 20 milliamperes divided by volts. So this is the value of transconductance. Now we will understand linear operation of transistor under the small signal condition. We know that collector current is equal to Is e raised to the power VBE divided by Vt. Okay, here this collector current and this VBE, they are DC quantities. Now if you are talking about both AC and DC quantities, it means now this equation becomes instantaneous collector current is equal to Is e raised to the power instantaneous base to emitter voltage divided by Vt. Okay, now as you can see here, the relationship between this collector current and this base to emitter voltage is exponential. So the IV characteristic curve looks like this. As you can see, the variable of x-axis is instantaneous base to emitter voltage and the variable of y-axis is instantaneous collector current. Now this is the exponential relationship between this VBE and IC. Okay, and this point is bias point Q and the coordinates of this bias point are DC collector current and DC base to emitter voltage. Now, as you can see here, this small signal base to emitter voltage is superimposed on this DC voltage, and it is represented by this triangular waveform. This small signal base to emitter voltage gives rise to small signal collector current IC, which is also represented by this triangular waveform. Now this small signal collector current is superimposed on this DC collector current, as you can see here. Okay, now we know that the formula of slope is y is equal to mx plus c. Here, as you can see, this is slope, and we know that this gm is transconductance. Okay, since it is a straight line, it means there is no constant here, and we know that here the variable of y-axis is instantaneous collector current, and this slope is transconductance, and the variable of x-axis is instantaneous base to emitter voltage. Okay, so this is the equation of small signal collector current in terms of transconductance, which we have derived in our previous slides. Now we will talk about small signal base current. We know that the relationship between DC collector current and DC base current is given by this equation. IC is equal to beta IB, where this IC and this IB, they are DC quantities. Now we are talking about instantaneous quantities. So this equation now becomes instantaneous collector current is equal to beta instantaneous base current. Now this is equation number 1. Now if we rearrange this equation number 1, we get instantaneous base current is equal to instantaneous collector current divided by beta. From our previous slides, we know that instantaneous collector current is equal to IC plus IC VBE divided by VT. Now, if we put this value of instantaneous collector current in this equation number 2, we get instantaneous base current is equal to IC divided by beta plus IC VBE divided by beta VT. Okay, if we rearrange this equation, we know that this IC divided by beta is equal to IB. Okay, so now this equation number 3 can be written as instantaneous base current is equal to IB plus IC VBE divided by beta VT. Okay, now we know that this instantaneous base current is the sum of this DC quantity and this AC or time varying quantity. It means this is small signal base current, which is equal to IC VBE divided by VT beta. Now we know that transconductance is equal to IC divided by VT. Now if we put this value of transconductance in this equation number 4, we get small signal base current is equal to Gm VBE divided by beta. So this is the equation of small signal base current in terms of transconductance. The small signal input resistance between base and emitter is denoted by R pi, and it is defined as VBE divided by IB. Now this is equation number 1. From our last slide, we know that small signal base current is equal to Gm VBE divided by beta. Now, if we put this value of small signal base current in this equation number 1, we get R pi is equal to VBE divided by Gm VBE divided by beta. Now this VBE is going to cancel this VBE. It means now this R pi is equal to beta divided by Gm. Now this is equation number 2, and as you can see here, this resistance is directly proportional to this beta. It means it is directly dependent on this beta. Now we know that this transconductance Gm is equal to IC divided by Vt. So now this equation number 2 becomes R pi is equal to beta Vt divided by IC. Now this is equation number 3. Now according to this equation, this resistance is inversely proportional to this DC collector current. Okay, we know that IC is equal to beta IB. It means IB is equal to IC upon beta. Okay, now if we put this relationship here in this equation number 3, we get R pi is equal to Vt divided by IB. Okay, it means now this resistance is inversely proportional to the DC base current. Now look at this example. If you have a bipolar junction transistor where collector current IC is 0.5 milliamperes, and if the manufacturer specifies beta to range from 50 to 200, and you have to give the expected range of transconductance, base current and input resistance at base. So how you are going to start your analysis? First we will find transconductance. We know that the formula of transconductance is IC divided by Vt. Here IC is 0.5 milliamperes and Vt is 0.025 volts. So the value of this transconductance is 20 milliamperes per volts. Okay, and it is constant. Now we will find base current IB. Okay, we know that IC is equal to beta IB. It means IB is equal to IC divided by beta. Okay, it means here this IB is equal to 0.5 milliamperes when it is divided by 50. We get base current 10 microamperes. Now if this beta is 100, this base current is 5 microamperes. Now if this beta is 150, this base current is 3.33 microamperes, and if this beta is 200, then this base current is 2.5 microamperes. Okay, now the range of this base current is from 10 microamperes to 2.5 microamperes for this range of beta. Okay, now we will find range of input resistance at base. Okay, we know that the formula of R phi is equal to Vt divided by Ib. Okay, so we know that Vt is 0.025 volts, and if this Ib is 10 microamperes, this resistance is 2.5 kilo ohms. When this Ib is 5 microamperes, this resistance is 5 kilo ohms. When this Ib is 3.33 microamperes, this resistance is 7.5 kilo ohms, and when this Ib is 2.5 microamperes, this resistance is 10 kilo ohms. Okay, so the range of this input resistance at the base is 2.5 kilo ohms to 10 kilo ohms. Okay, so this is your answer. Now we will talk about small signal emitter current. We know that the relationship between DC collector and DC emitter current is given by this equation. IC is equal to alpha IE, where this IC and this IE, they are DC quantities. Okay, now we are talking about instantaneous quantities. It means now this relationship can be written as instantaneous collector current is equal to alpha instantaneous emitter current, and if we rearrange this equation, we get instantaneous emitter current is equal to instantaneous collector current divided by alpha. Now we call this equation equation number 1. We know that the equation of instantaneous collector current is equal to IC plus IC VBE divided by VT. Now if we put this value of instantaneous collector current in this equation number 1, we get instantaneous emitter current is equal to IC divided by alpha plus IC VBE divided by Vt alpha. Now if we rearrange this equation, we know that IE is equal to IC divided by alpha. Now this is equation number 2. Now if we put this value of IE here, this equation becomes instantaneous emitter current is equal to IE plus IC VBE divided by Vt alpha. Okay, so this instantaneous emitter current is equal to the sum of this DC emitter current and this AC or time varying emitter current, which can be written as IE. It means this is an AC quantity which is written in lowercase with lowercase subscript. So this small signal emitter current is equal to IC VBE divided by Vt alpha. Okay, now we know that transconductance is equal to IC divided by Vt. It means the small signal emitter current is equal to Gm VBE divided by alpha. Okay, So this is the equation of small signal emitter current in terms of transconductance. Now, in this case, the small signal resistance between base and emitter is denoted by Re, and it is defined as VBE divided by IE. This is equation number 1. We know that this small signal emitter current is equal to GM divided by alpha. Now, if we put this value of small signal emitter current in this equation number 1, we get Re is equal to VBE divided by GM divided by alpha. Now this VBE is going to cancel this VBE. It means here this resistance is equal to alpha divided by GM. Now this is equation number 2, and according to this equation, this resistance is directly proportional to alpha. It means it is dependent on this quantity alpha. Now we know that GM is equal to IC divided by VT. Now in this case, this equation number 2 becomes Re is equal to Vt alpha divided by IC. This is equation number 3, and this equation shows that this resistance is inversely proportional to DC collector current. Now we know that IC is equal to alpha IE. It means IE is equal to IC upon alpha. So now this equation 3 becomes Re is equal to Vt divided by IE, and this is equation number 4, and this equation shows that this resistance is inversely proportional to DC emitter current. Okay, so this is the small signal resistance between base and emitter when you are looking into the emitter. Now here this R pi is the small signal input resistance between base and emitter when you are looking into the base, and this Re is the small signal input resistance between the base and emitter when you are looking into the emitter. So what is the relationship between these two resistances? We know that Re is equal to alpha divided by transconductance. We know that this alpha is equal to beta divided by 1 plus beta. Now if we put this value of alpha in this equation number 1, we get Re is equal to beta divided by 1 plus beta multiplied by transconductance. Okay. Now we know that R pi is equal to beta divided by Gm. It means Gm will be equal to beta divided by R pi, and 1 upon Gm is equal to R pi divided by beta. Okay, this is equation number 2. Now if we put this value of 1 upon Gm here in this equation number 2, we get Re is equal to beta divided by 1 plus beta multiplied by R pi divided by beta. Now this beta is going to cancel this beta. It means here Re is equal to R pi divided by 1 plus beta, or R pi is equal to Re 1 plus beta. So this is the relationship between Re and R pi. Now look at this example. If you have a bipolar junction transistor where beta is 100 and collector current is 1 milliamperes, and if you want to find transconductance Re and R pi, so how you are going to start your analysis? First we will find transconductance. We know that transconductance is equal to collector current divided by thermal voltage. Here this collector current is 1 milliamperes and we know that the value of thermal voltage is 0.025 volts. After solving this, you will get 40 milliamperes divided by volts. Okay, so this is your transconductance. Now we know that the formula of R pi is equal to Vt divided by base current. We call this equation 1. Okay, now we know what is the value of thermal voltage, but we don't know the value of this base current. But we know that the relationship between base current and collector current is given by this equation, and from this equation base current is equal to collector current divided by beta. Here this collector current is 1 milliamperes and we know that beta is 100. So after solving this you will get 10 microamperes. So now you have the value of base current IB. So if we put the values of thermal voltage and base current in equation 1, we get R pi is equal to 0.025 volts divided by 10 microamperes, and after solving this you will get 2.5 kilo ohms. Okay, this is the value of R pi. Now we know that Re is equal to R pi divided by 1 plus beta, and here we know that this R pi is 2.5 kilo ohms and here this beta is 100. Okay, so after solving this you will get 24.75 ohms and it is approximately equal to 25 ohms. Okay, so this is your answer. Now we will understand the relationship between this input resistance R pi and this input resistance Re in terms of current. From the formula of R pi, we know that R pi is equal to VBE divided by IB. It means VBE is equal to IB R pi. This is equation 1. From the formula of Re, we know that it is equal to VBE divided by IE. It means VBE is equal to IE Re. Now this is equation number 2. Now if we compare equation 1 and equation 2, we can write it like this: IB R pi is equal to IE Re. Here we are comparing equation 1 and 2. Okay, now if we rearrange this equation, we get R pi is equal to IE divided by IB and this term is multiplied by Re. Okay, so this is the relationship between R pi and Re in terms of current. That's all for today. Now what are the key takeaways of this lecture? In this lecture, you derived equations of small signal base current, small signal collector current, and small signal emitter current. In this lecture, you also understood what is transconductance and you also studied about small signal resistance between base and emitter, looking into the base, that is R pi, and looking into the emitter, that is Re, and you also understood relationship between these two resistances here.
Thank you for watching this video. If you have any questions, then write your questions in comment section of this video. Don't forget to subscribe our channel and share it with your friends and family. Thank you.